Okay, rotational inertia. This is an example we tested in class. We have a solid disc and a hollow hoop, and we want to know which one's going to make it down this ramp first. And this is a question of rotational inertia. Remember, inertia is an object's resistance to changes in its motion. Right now, somebody is holding those up there. They're invisible, but they're there, holding these objects in place. So these objects want to remain held in place, all right? Inertia is an object's laziness or its resistance to changes in its motion. And of course, those changes come from an outside force. What force is that in this case? Well, it would be gravity. Once whoever's holding it lets go, both of these objects will be pulled by gravity down the ramp. Which one's going to be more sluggish is the question, and which one is going to be quick to get down the ramp. And most of you can remember that the solid disc is the one that gets down the ramp first, and the hoop lags behind. But why is that? And the answer is that it has less rotational inertia, less Ri. The solid disc has less rotational inertia. And why is that? It's because the bulk of mass in the disc is close to the axis of rotation. Okay? Whereas in the hoop, this has more rotational inertia because the bulk of the mass is as far away from the axis of rotation, which is right there, as it can get. All right? The bulk of the mass is far from the, I'll just say mass is far from axis of rotation. So when these two things are released, this one has less rotational inertia, therefore it's like, giddy up, I'm getting out of here, I'm going down this ramp, and I'm going to get there first. The hoop stretches its legs for a second and then starts to roll down the ramp. Meanwhile, the solid disc is gone. Once they get across the floor and they go down the floor, they'll roll at similar velocities depending on what the friction of the floor is. But then if they were to roll up a ramp on the other side, both of them would reach the top at the same time because the hoop has more rotational inertia. So once it starts to go up, it says, I'm going up, but I have more rotational inertia. I don't want to slow down, even though gravity is now pulling me back down this ramp. I'm headed this direction. It takes longer for me to slow down and stop, whereas the hoop starts to roll up. It's got a little more velocity, but it says, I'm going to slow down quickly because that's what I do. I've got low rotational inertia. So both the hoop and the disc would get to the very top at the same time in this case. Now there's questions about the clown riding a unicycle on a high wire. Here's the tightrope, and here's the clown riding on this bike, and he's got a long pole. All right, and the long pole is meant to do what? Well, here's the clown, and the pole does what? Well, it moves mass away from the axis of rotation. And the question, I think we put some masses on the end there, and we want to know what are 3 ways that this guy is able to be stable riding across this tightrope on a unicycle with a long pole with weights on the end. And the answer is primarily because of rotational inertia. One is Ri. And how does he have more rotational inertia when he's got this long pole? And that's the reason for it. By bringing mass away from the axis of rotation, which in this case would be right here. If this thing were to rotate, this bike would rotate, and him with it would rotate down and to the alligator pit down here below, which we hope doesn't happen. But he would rotate around the wire. The wire and the connection between the bike tire and the wire is the axis of rotation. So by moving mass away from the axis of rotation, he has increased his rotational inertia, which is going to make it less likely that he'll rotate. And if you ever see tightrope walkers, they often carry a pole like that. And I always wondered when I was a kid, isn't it hard enough to walk across a wire? Why on earth did they make them carry that pole too? But in fact, the pole helps because it increases that person's rotational inertia, makes them less likely to rotate. The second thing that makes this easier for the person is that this bent pole here has masses on the end, and those will in effect lower the center of gravity. Okay, if the weights bend down, then his center of gravity, which would normally be up here somewhere, is now lowered to below the wire. And if that's the case, then we would say that he's in stable equilibrium, and it will take work to make him rotate. So by lowering the center of gravity, you become more stable, and that is important. Lower CG is more stable. If the CG is actually below the wire, then he's in stable equilibrium, and it will take work to make him rotate. And then the third thing is probably the least obvious, but that's the tire. The tire is spinning in a plane, a vertical plane, and it therefore has angular momentum. And that's very important, because if you've ever tried to sit on a bike that is not rolling, then you know that it's almost impossible. But once you get rolling, then the tires, they want to continue spinning in that same vertical plane, and it takes a torque to get them out of that plane. So by having the bike tire moving, the tire is actually helping him stay on a vertical, or in a vertical plane, and it is less likely that he will rotate and fall off of this thing. So the spinning bike tire gives him angular momentum, gives the tire has angular momentum, therefore it continues to spin in the same plane and makes it less likely that he will topple over and fall to his death with the alligators. All right, more rotational inertia because of the bar, lower CG because of the weights on the bar, and angular momentum because of the bike tire. Don't try this at home.